Right. So this is a lecture number 5, and we're starting by answering a homework question. I had already answered one, question 4, and I didn't record it. So we're starting the recording now for question 3. So it says a fair coin is flipped 10,000 times. The first 4 flips are heads. It says fill in the following charts, giving your best prediction for what will happen after the given number of flips. So we did a question like this in class. What you see is as follows. The percentage of heads after 10 flips is 70%. Correct?
Correct.
After 100 flips, it's 52%. After 1,000 flips, it's 50.2%. After 10,000 flips, it's 50.02%. So it certainly seems that as the number of flips is getting larger and larger and larger, our percentage of heads that we have from our experiment is getting closer and closer and closer to the true value of 50%.
Yeah.
Right? We keep getting closer to it, right?
Right.
This is the law of large numbers, which says, essentially, that as the number of trials gets larger, your empirical value should get closer to the theoretical value. The value based upon your data, your experiments, should get closer and closer and closer to the true value, whatever it may be. Okay,
So would it be okay to say, so basically the law of large numbers, is that basically just saying like, we're given time? And so kind of going back to question 4 was, is it basically asking us, is 10,000 times enough times to say that we're getting to our accurate value that we want?
Not exactly, but you could ask yourself that question. Is 10,000 enough?
Right, and I would say yes.
And you would say yes, right? Okay, how about 1,000? Was 1,000 enough?
I would say yes to that too.
Okay, was 10 enough?
No.
No, 70% is way off, right?
Right.
So it took a large number of numbers before you can say that I'm fairly close.
Okay.
And this is essentially the law of large numbers, that as a general rule, it's going to take lots of runs before you can say that you're close.
Okay.
Okay,
Right.
now we're going to actually come up with a formula today, if we get that far, to determine how many runs we need to be however close you want to be. If you say, I want to be within 1%, we're going to say, do this many runs. And if you say, no, I'm okay with 2%. Okay, do this many runs. I'm okay with 5%. Okay, fine, do this many runs. We're actually going to come up with a formula for that.
Professor, I have a question.
Yes.
So on number 3, it says that the first 4 flips are heads.
Right. So of the next 6, you're going to have, you expect 3 more heads, correct?
Yeah, but I'm just really confused on for the first column where it says 10. Why is there a 7? Like, I don't understand how we're supposed to like estimate. Like, because I understand that it's like either heads or tails, and that's why when you get to 10,000, it's closer to 50%. Right. But the first estimate where it says 4, it should be 4 heads, right? Because it says number of heads is 7.
Well, one second. The first 4 flips were heads, correct?
Mm-hmm.
Now, flip it 6 more times.
Mm-hmm.
How many heads are you going to get in those 6 flips?
Oh, probably half.
Probably half, right?
Like,
3.
So 3 more, right? For a total of 7.
so that's how you would come up with predicting. Because yeah, I was confused about the 7. How do we got the
Right?
7 there too?
You
but now I
already
understand.
you already have 4.
Uh-huh.
You're flipping it 6 more times.
Uh-huh.
You expect it to be 50-50, so in 6 flips, I'll probably get 3. So those 3 together with the first 4 make 7.
So don't look at it as like 10 flips.
No. It's
If
not
they gave
just
us-
10 because the first 4 are already done.
Right.
The first
Okay.
4 are done and we already have those. It's the next 6 that we don't know,
Yeah, that makes sense.
right? So the next 6, 3 of them heads, 3 of them tails. That's probably what's going to happen. Is it possible that I'm going to get 6 more heads? Sure, it's possible. But the question is, what is the most likely outcome? What do you expect to happen?
So we get the theoretical probability for the next
Yes, exactly. You can't use empirical for what's going to come next.
Because that's what we're figuring it out.
That's what you're trying to figure out. So empirical is based upon what I've done.
Okay.
Theoretical is what does theory tell me it should be.
Okay, got it. That makes me understand way better, because like, how did that 7 appear?
Yes, that's exactly it. The first 4, they're set in stone. You can't change them. They actually happened.
Okay.
And now we have 6 flips, and of those 6, I expect 3 and 3.
Okay, got
The
it.
4 that I already have, the 3 more, that makes 7.
Okay.
And for the next one, I have 100 flips, right? I've already done 4, but I have 96 left. Right? I have 96 more flips to go, correct?
Mm-hmm.
Of those 96, how many heads do you think you're going to get?
96. Let me use my calculator because
No problem.
48 plus the 4 that you already have.
Probably 48 plus the 4 that I already have. That's 52.
That makes sense now.
Right? And for the next one, which is the thousands, I've already done 4, which means I have 996 flips left. Of those 996 flips, how many heads am I going to get? How many heads do you expect me to get? That's a better way of saying it.
498.
Plus the 4 that I already have.
Plus the 4. It'll be 502.
And that's where they get to 502 from.
Yeah.
Right? And this is the same idea for all of them. So notice that if you just take into account what you expect, the numbers get closer to 50%. And the way the world works, the law of large numbers actually works. It's just one of those weird things. In the world, things get closer to what you expect. So you're not going to have these specific numbers in general. You're not going to have 7 every time and 52 every time and so on. But whatever situation you actually do, they will keep getting closer and closer to 50%. And the further out you go, the better it's going to get. So, answered a couple questions, but we have what to do. So what's going to happen today is we are going to finish the second chapter. I don't think, have we been the third one? We're still on simulations, right?
Yeah.
We haven't finished the second chapter, correct?
No, we haven't.
All right, because my other class did, but we lost a day because of Labor Day, which means now you guys are behind. It used to be that I would do whatever I did with you, I would then do with them to keep you guys in sync. But now it's the opposite. Whatever I do with them, I have to do with you. So let's continue from where we left off. We were, I believe, does it make sense to say that we were on slide
16.
16? Is that where we left off?
Yes. Yeah, 16.
Okay, so we're not going to do the next example, only in the interest of time. I do want to turn your attention again to slide number 20. And I'm not so worried about where this data came from. I just want to illustrate once again the feature that I've stressed multiple times, that when you have a graph like this that uses your data to calculate the probability, what essential difference do you see between the left side of the graph and the right side of the graph? Can you show the power? You don't have the PowerPoint, Karen? Yeah, I'd rather be able to see you guys. When I share, I can't see you at all. I just see the PowerPoint. I'd prefer to do it this way. If you can load up your PowerPoint, which is why I'm sharing.
What slide are we on?
No, we're on slide number 19.
19.
And if clarification is needed where I have to draw on it and label things, then I will share my screen for those times. But as a general rule, until that's necessary or until anyone asks for clarification on something, I prefer to see you and have you guys be looking at the PowerPoint.
Are we looking at 19 or 20?
19, the graph. I think it's not. Oh no, 20. I'm sorry, 20. The graph on 20.
What?
Thank you. So if you look at this graph, so again, I ask a question: what is the essential difference between the left side of the graph and the right side of the graph?
The left side is a lot more chaotic.
Lovely. I heard the word erratic before, then the word chaotic. It's all saying the same thing. We have a lot of fluctuation in the beginning. And then what occurs as we go to the right?
It levels out.
We have stabilization. It levels out. Okay. What value does it seem to be leveling out at?
35%.
50.
No, 50. No, it's not 50. 50 is not even close.
250. 250.
35.
Wait, 1 second.
100?
Wait. Hold on.
What?
Where are you looking that you see 250? Because okay. No. What you're saying is at how many runs does it start to level out?
Oh, okay.
Right? It
It's like
roughly,
35, 36.
okay, so it seems to start between 150, 200, 250. That's about when it starts to level out. But what value does it approach?
Mhm.
What percentage does it approach?
Yeah.
35.
0.35.
It seems to be roughly 35, 36%, correct?
Right.
Yeah.
Okay, but here's the thing, and that's right. I'm not saying that's wrong. But if you look at the next slide, slide 21, what we see on slide 21 is a new
Whoa.
graph. Does this
Oh.
graph look like it's stable?
No.
No, not at all.
No.
But this is just a zoomed in version of the previous graph for the last 100 runs. Right? This is just the previous graph that you said was stable. This is the same graph for the right side, the last 100 runs. Like, how's it labeled? This close-up of the graph shows only the last 100 runs. But look at those values on the left side. Those values are offset by what? The third decimal place, correct?
Yes.
Mhm.
When you zoom in really close.
They're really close to each other.
Yeah, but everything's gonna look chaotic when you zoom in close enough. You know, when you get to the 1,000th place, you know, things that look stable from, right? Think of a glass of water. Who here has taken chemistry before? Right? A few of you have taken chemistry, right? If you look at the glass of water, does that water look smooth and continuous and pretty much uniform throughout the entire glass? You look at it, does it look like it's the same everywhere?
Yes.
Now, zoom in to the molecular level.
No, it's not.
Okay, it's going to look like these bonds and atoms, and there's space in between. And right, when you zoom in far enough, even things that look smooth and simple are going to fluctuate. So it's very important to keep your eye on the scale. Okay, if you zoom in, be aware of that, how close you're zoomed in. So let's answer the questions on this slide. First, it says, what was the result on the last run? Was the last result a yes or a no?
It was a no.
How do you know that it was a no?
Because
Going
it went downwards.
Because it went down. And this is like from the very first day, correct?
Mhm.
Yeses, it goes up. No's, it goes down.
Mhm.
How much did the percentage change had we stopped at 499 instead of 500? If we would have not done that last run, how much would the percentage have changed? What was it at 499 and what is it at 500? If I would have stopped at 499, what would have been my final value that I would have used?
0.356.
0.356-ish. Was it more than 0.356 or less than 0.356?
Slightly less.
If I would have stopped at 499?
Let's see, 0.34, 35674, probably something
Oh,
like
I'm
that.
It
looking
would
at
have been a little higher, correct?
what?
Hold on, let me share because I guess you
You
guys.
say it changed by like 0.002.
Hold on. This is one of those situations that people are not seeing it. I want to demonstrate. Can you all see my thing here?
Yep.
Let's get you people out of here. Okay, so this here, this one right there, that was run number 499. That one. That was run number 499. And this one right here, that was run number 500. Do we agree?
Yes.
When I stop at 500, the value is 0.356. That's the value at 500, right?
Mhm.
But had I not included this, I would have stopped here at 499. And the value at 499 is a little bit higher than 0.356. Maybe it's 0.356 or so. Do you see that?
Yeah.
Yeah.
Which means when I included the 500th run, it dropped by 2/10,000th. That's a very tiny change. I mean, even though it looks like this thing is all over the place, 2/10,000th. That's 0.02%. That's minuscule. Does that make sense?
Yeah.
Very, very small. So by how much did the results change on the last one? 0.0002 or so, a very tiny amount. Next question. What was the smallest estimate during this entire last 100? What was the smallest value I ever could have gotten? If I would have said, I'm done, I'm not doing more, I'm stopping here. What's the smallest it ever would have been along these last 100 runs?
0.348.
Excellent. Excellent. 0.348 right here at run number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At the 412th run, because remember, this is just the last 100. At the 412th run, on the bottom left of the graph, hopefully you all see what I'm talking about. But right here, right there, if I would have stopped there at the 412th run, I would have ended up with a value of 0.348, 34.8%. What's the highest that I could have stopped at, and I stopped at anywhere amongst these 100 runs?
0.36.
Around
0.3642.
460, just past it.
So right there at about 0.3642 or so,
Yeah.
36.42%, give or take. So what you see is that the smallest to the largest was about 1.5% difference.
That's a pretty big difference.
Well, 1.5% is big in the grand, compared to 100%. That's true. But if you're trying to get a general idea of the percent of people who approve of something,
Then it's not that big. But like on a
not-
small scale like that, it's pretty big difference.
right? No, I understand. Right, it is pretty big on this graph. But it depends on how accurate you want to be, and we're going to come up with a formula very soon for how accurate we want to be. Does that make sense so far, though?
Yeah.
Okay, so again, I've really focused a lot of time in the first couple of weeks on stabilization and these graphs of computing probability and having a lot of erraticity and chaotic behavior in the beginning, followed by stabilization via the law of large numbers. So let's now go ahead. We're not doing every slide. We just don't have the time, unfortunately, but let's turn to slide number 23. How many runs? How many runs should you do in a simulation? So the answer is, there's a formula for it, but it's not just, oh, let me plug in the formula 12 and there's my answer. 100, there's my answer. 1,000, there's my answer. It depends on you. Essentially, the question is, how close do you want to be to the true value? So let's read this boxed slide. It says, according to the law of large numbers, the more runs you do, the closer your estimated probability is likely to be to the theoretical probability. In practice, people use statistical software to conduct simulations. And when using software, you can do as many as you want. You can do 1 million runs and your computer will spit out the answer in seconds. Why not do it if it takes that little time? However, in grades K through 8, simulations are done by hand. Why do we do them by hand? so that students can get a feel for the process, okay? In that case, you can't do a million observations, right? We just don't have the time. So we have a basic rule of thumb. It says, how confident do you want to be in your answer? If you want to be within an error E, like 1% or 2% or 2.5%, if you want to be with an error at most E, then what you do is you do 1 over E squared. So let's do an example of that very quickly. I'm going to share again so you can see what I'm doing. So annotate. So let's say that your error, how close you're willing to be to the correct answer, is 1%, 0.01. I want to make sure that I am within 1% of the correct answer. So the number of runs that I'm going to have to do is going to be 1 over that number, 0.01 squared. And this is something that we will certainly use a calculator for it, because doing it by hand is not the simplest thing. I mean, it's great if you can, but I'm not going to require. What is
So
it?
you're saying, sorry. So if we want it to be within 1%,
Right. So if you want to be,
it would be,
if you want your final answer, because remember, even with stabilization, there's always going to be a little bit of fluctuation, correct?
right.
So because there's a little bit of fluctuation, you're never going to know for certain whether your answer is correct. There's always going to be some error. You want to minimize that error as a general rule. You want the error as small as possible. The only way to make the error 0 is to do infinitely many runs, but we don't have the time for that. So we got to do a finite number, 100, 1,000, 10,000, a million, whatever the case may be. There's always error. You decide what error you're willing to accept for whatever experiment that you're doing. If you say, I'm okay with a 1% error, then you plug 1% into this formula and you do the math. What is 1 over 1% squared?
100.
It is not 100.
What? 0.1 squared is 0.01.
I didn't say 0.1 squared, 0.01 squared.
Oops.
Yep. Oops, it is. So what is it?
10,000 runs.
10,000 runs. If you want to be guaranteed, not guaranteed, but if you want to be pretty certain that you're going to be within 1% of the true value, then you would want to do 10,000 runs. Let's say you say, 1%, that's great, but I can't do 10,000 runs. So I'm going to be happy with 3%. If you say I'm happy to be within 3%, how many runs would you need to do? If you decide that you're happy with a 3%, as long as I'm within 3% of the true answer, I'm happy. How many runs do you need to do to be within 3% of the true value?
1,111.
Well, you're close. Because if you did it correctly in your calculator should not read 1,111. Your calculator is going to read 1,111.1111111 forever, correct?
Yeah, it does. I just thought I would run that.
I know, but here's the thing. Here's the thing. You have to round because you can't have 0.1 trials, correct?
Right.
So the question is, which way do you round? Do you round down to 1,111 or do you round up to 1,112?
You would round up.
You always round up because more trials is never worse, right? It's never a bad thing to do more trials. So sharing again, if I want to have an error of 3%, 0.03, then the number of trials which is 1 over 3% squared, gives me 1,111.1111 forever, which then becomes 1,112, because you always go up, you never go down. Why always up and not down? Because it's never a worse thing to do more trials. The worst that can happen is you get a better approximation. And if that's bad, then you don't know statistics very well. We want a better approximation.
How did you get the 0.3 if it's 3%?
It's not 0.3, it's 0.03.
Yeah, 0.03. How did you get that?
Because 3%, you move the decimal 2 over. So 3 points, 0.3, 0.03.
Okay, thank you.
Right, 3% is a 2 decimal place move. Does that make sense?
Is it always over one, or is one always?
Yes, one's always on top. That's the rule. 1 over the error squared.
Okay, thank you.
Okay, that is the rule. Okay,
You always move the decimal place 2 points to the left?
that's correct. When you're switching from percent to a decimal, you always move it 2 places to the left. And if you're going from a decimal to a percent, it's 2 to the right. It's always 2. Does that make sense?
Yes.
Okay, so we have finished the second PowerPoint, which means the chapter 2 homework is due a week from today. We'll have a quiz on that as well a week from today.
Oh no.
So sorry?
I was just saying, oh no.
Yeah, no, quizzes are good. They let us demonstrate our knowledge. We should be very happy when we get to take quiz.
Is it
Who
a
here,
week
who
today
here
or-
does not like to show off what they know?
Not in math class, I don't.
Okay, well, that's something else.
This is where I doubt myself.
Sorry, what was that?
I love to do that, but this is where I doubt myself.
Ah, so
Yeah.
this is where we need to work on ourselves, right? And to get better.
Yeah, this is the
How do we
one
get,
class where
you
I'd
don't
rather,
get better without fire, huh?
this is the one class where I'd rather not show off.
I see. I see. Well, I guess in the immortal words of someone a lot smarter than I am, tough shit. That's basically what it comes down to. So unfortunately, we are, Wednesday will be a week from today. Did I not say it was a week from today? Right?
Yeah, you said
Yeah,
a week from
you did.
today. Yeah.
A full week, right? The homework's still a week from today, and we'll have a quiz. I'm not sure how to do it on Zoom. I don't know what you mean by it. And no follow-up, so I don't know what he meant. But okay, so it'll be a week from today. I will put the solutions up Monday or Tuesday so that you can go over them. I mean, show what I don't know how to show what I know. Well, either do I, apparently. So I'm working on it as well.
Professor, is there any way that we can get the solutions up before those days? I know we don't want to get the answers before that, but I mean, I don't know if it's for everybody else, but for me, I just like I did for this homework, I didn't do 3 and 4 because I wanted to see if I could work it out by looking at the solution.
That's exactly what you should be doing. And I feel that if I would have give you the solutions too soon, you'd be tempted to look at the answer right away and not really work at them, which is why, I mean, I want you to understand my reasoning for what I did.
No, I understand.
I feel if I would have given you the answers earlier, you would have gone to the answers earlier. And
Right.
not worked as hard trying to figure it out yourself. And maybe, and if you say I'll work on it, that's fine. Okay, then do that next time too, and you'll be fine. But it's a temptation when the answers are there. I know it. It's the same with me.
For me, it's just because the weekends are the time for me to study.
Okay. Well,
And
listen.
so then,
I don't mind having the second quiz the following Monday after the weekend. I don't mind that. We can discuss that. But
Okay.
I certainly want to give you time to work on it
right.
prior to seeing the answers.
Okay.
Okay. So we can certainly discuss that. I don't care really when we have the quiz, as long as we eventually have the quiz. So that's number one. So we finished number 2, and there'll be a quiz in it, and the homework. You have the homework. It's on the PowerPoint, so you can get started on that immediately. And now it's 7:40. So for the rest of the class, it's going to be the quiz. And here's what it's going to be. Very, very straightforward. I'm not going to require you to be on camera. In fact, I'm not even requiring you to stay in the room. I will trust you that when I give you this particular problem, you will not look at your answers. You will not look at my answers, but you will do it as if you've never, well, if you have no resources handy, because I'm just going to pick one from the homework. So you've already done it, hopefully, and I've given you my answers, so you can just, in theory, look at them. I am trusting you not to, so that your work is just basically like you've never seen the problem before. You just sit down and you're doing it. You can just do it on a piece of paper, or you can make, if you have a photocopy machine, you can print it out. I don't care. But I want you to either send it to me via Canvas or my email, any one of my 12,000 emails. Yes, Talara?
Sorry. So will all quizzes be like that, where it's one problem from the homework and
Most likely. But if I start to get the feeling, that people are just copying, and that, again, I'm not going to have any proof, but it'll be a feeling, then yes, then the questions I can make up new questions.
Question. How do we submit it through Canvas? Do we like message?
Yeah, you can, if you email me on Canvas, you should be able to attach it.
Okay.
So if we're working on,
if you can't figure that out, just email it to me. That'll get to me as well.
Okay.
with a picture and just.
Is it due before 8:15 then?
Yeah, a half an hour is more than enough time. So I like it before 8:15. And I decided that I'm going to pick question number, because remember, I'm Jewish, so I love pigs. Question number 2.
Okay.
Okay, that was the pig question, right?
Yeah, side dot 1, I think. Yeah.
I think, the pig, I think it was the pig question. Question number 2.
Okay.
Okay, so again, please, don't, I mean, hopefully you already did it and understood it and saw my answers, so you really understand it. But at this stage, the goal is not to just copy an answer, but to recreate it as if you were seeing it for the first time. You have a half an hour. You do not have to stay in the classroom. In fact, I'm going to go, so that way you can go as well. Okay, and please email to me or Canvas message it to me on any of my emails before 8:15.
Are you gonna upload like a different thing for number 2? Like, how are you uploading?
Yeah, if you don't want to.
No, just open the PowerPoint that you already have and just do it. I'm not sure what you're asking.
Okay, so go in from the first chapter where the answers weren't, and just read.
Exactly. The one with the answers were not there. Yes, go ahead.
So then it's basically the same question on number 2, right?
Exactly the same question.
Wait,
So
I have another question. Oh, sorry.
Oh, 1 second. Yeah, it's exactly the same question.
So if we already did it, then we could just take a picture of it and send it to you?
No. What you already did, you did for homework. That was your homework. I don't want you to.
He wants you to look at the blank one with no answers.
Do it again from scratch without looking at any of your previous work that you've done.
Okay, understood.
Okay, don't just copy. Don't just take a picture of the homework. That was homework. This is the quiz.
Okay.
Now I have no proof, but I'm asking you to do it that way.
Okay.
You do not have to write the question because I know what the question was.
Okay.
Okay.
So we just label it maybe quiz number 2.
Yeah, quiz number 1, the dates, your class, social security number would be great. Other than that, everything is fine.
Can we start the quiz the moment that you get off? Because right now
you could have finished it by now if you started already. Just go ahead and begin. Go ahead and do it. Go ahead and do it.
Do you label for it ABC?
Yeah, ABC, the whole thing.
ABC to do like each part of it? Okay.
Yeah, the whole thing.
Is it okay if I use the blank template of
totally
the
fine.
homework? Okay.
Totally fine. Totally fine.
Can I write it on the scratch paper?
Totally fine.
Yeah.
Totally fine. Scratch paper works too. I'm okay with either one.
All right. Thanks, Professor.
You're welcome. And again, if you can just go. You don't have to be here to do it. I'm trusting you to do it off camera. But again, if I start to get the feeling that people are being a little dishonest, then then it'll be on camera and there'll be new questions, and of course that'll be worse for everyone. Just email the quiz. When you're done, you can just email it or Canvas message it, either one. Otherwise, you're free to go. I'm going to stop recording.